You open your phone. Tap on your Maps app. Within seconds, a tiny blue dot appears, telling you exactly where you are, even if you're in the middle of nowhere. You drop a pin, ask for directions, and like magic, your phone guides you turn by turn with astonishing accuracy to wherever you want to go. But have you ever stopped to ask, how does that actually work? How does your device know, within meters, where you are on the entire surface of a rotating planet without asking you? The answer lies not in your phone, but far above your head. Orbiting the Earth at thousands of kilometers per hour are dozens of satellites, each constantly transmitting signals that your phone listens to. This global system, invisible to the naked eye, is the reason your blue dot works. It's called the Global Positioning System, or GPS. And it's one of the most powerful technologies humans have ever created. But GPS isn't just for maps. It underpins modern life in ways most people never notice. It's in agriculture, aviation, finance, shipping, military systems, disaster response, and even the power grid. Remove GPS, and entire industries grind to a halt. So how does it actually function? What's the engineering behind it? And how did we even manage to build a system so vast and precise? The story of GPS begins with the Cold War. In 1957, when the Soviet Union launched Sputnik, the first artificial satellite, American scientists noticed that the satellite's radio signal shifted as it passed overhead. This was due to the Doppler effect, the same phenomenon that makes a siren sound different as it moves past you. They realized that by measuring that frequency shift, they could determine the satellite's speed and location. But they also realized the reverse was possible. If you knew where the satellite was, you could determine your location on Earth. That was the spark. Over the following decades, the US military developed a satellite-based navigation system. By the 1970s, they launched the first satellites of what would become the Navstar GPS constellation. By the mid-90s, the full system was operational and free for civilian use. Today's GPS network consists of at least 24 core satellites, though more are in orbit. These satellites fly in 6 different orbital planes, about 2,200 kilometers above the Earth, completing 2 full orbits every day. Each satellite carries an atomic clock, accurate to a few billionths of a second. Why? Because time is the secret ingredient that makes GPS work. Here's how it happens. Each GPS satellite constantly broadcasts a radio signal. This signal contains the satellite's location and the exact time the message was sent, according to its atomic clock. Your phone listens for these signals and notes the time they arrive. Since radio waves travel at the speed of light, the time delay between when the signal was sent and when it was received tells your device how far away the satellite is. With one satellite, your phone knows it's somewhere on a sphere with a certain radius. With 2 satellites, that narrows it down to a circle, where those 2 spheres intersect. With 3, you get 2 possible points. And with 4, your phone can pinpoint your exact location in 3-dimensional space: latitude, longitude, and altitude. 4 satellites also allow the phone to correct for any error in its own clock by syncing with the more accurate atomic clocks in orbit. This process is called trilateration. Not to be confused with triangulation, which uses angles. Trilateration uses distances. It's an elegant dance of geometry, physics, and synchronized timing. And it happens continuously, dozens of times per second, all around the globe. But it's not easy. GPS signals are incredibly weak. By the time they reach Earth, they're about as strong as the background noise of the universe. Your phone's antenna has to be extraordinarily sensitive to pick them up. And that signal must pass through the ionosphere, weather systems, and even buildings, each of which can bend, slow down, or reflect the signal, introducing errors. To correct this, engineers developed clever solutions. One is differential GPS, which uses ground-based reference stations to detect and correct local errors. Another is assisted GPS, or AGPS, where your phone uses cellular networks and Wi-Fi data to quickly estimate your location before locking onto satellite signals. There are also satellite-based augmentation systems, like WAY-AS in North America, that provide real-time corrections for aviation and other high-precision needs. Still, the most impressive aspect is the clocks. Timing is everything in GPS. Even a tiny error of 1 microsecond, 1/1,000,000th of a second, means a positional error of 300 meters. That's why atomic clocks are essential. The satellites use rubidium or cesium clocks, synchronized to coordinated universal time. These clocks are constantly monitored and adjusted by ground control stations spread across the globe. These control stations, operated by the U.S. Space Force, manage satellite positions, health, and timing. If a satellite drifts or its clock wobbles, commands are sent to fix it. It's a tightly orchestrated ballet between space and Earth, 24/7, ensuring that the system remains reliable and precise. But GPS isn't the only game in town. Other countries have built their own satellite navigation systems. Russia has GLONASS. Europe operates Galileo. China has Beidou. Each of these systems works on similar principles, timed signals from orbiting satellites, but adds redundancy, regional improvements, or strategic independence. Most modern smartphones can use signals from multiple constellations simultaneously, improving accuracy, especially in urban areas or difficult terrain. The applications are nearly endless. In agriculture, farmers use GPS-guided tractors to plant and harvest with centimeter-level precision, saving fuel, time, and seed. In logistics, shipping companies track trucks, ships, and planes in real time. In finance, trading systems use GPS to timestamp transactions down to the millisecond. In telecoms, GPS provides the timing needed to sync cellular networks. And in disaster response, GPS helps rescuers locate victims, coordinate teams, and map damage zones. GPS also plays a key role in spaceflight. Launch vehicles use it to guide their ascent. Satellites use it to maintain orbit. And even space telescopes rely on GPS to align themselves with exquisite precision. Without it, much of what we know about the universe would be harder, if not impossible, to discover. But as GPS becomes more critical, it also becomes a target. Spoofing and jamming are real threats. A GPS jammer can block signals in a localized area, confusing vehicles, drones, or phones. Spoofing, meanwhile, involves sending false signals that mimic GPS, tricking a receiver into thinking it's somewhere else. These tactics have been used in military conflicts, smuggling operations, and even by privacy-conscious individuals. To counter this, engineers are developing encrypted military signals, multi-frequency receivers, and AI-based anomaly detection systems. There's also the question of redundancy. What if GPS went offline, temporarily or permanently? Some countries are investing in ground-based backup systems, such as ELARAN. Others are exploring inertial navigation, using gyroscopes and accelerometers to estimate position without satellites. But the truth is, our world is deeply reliant on GPS. A major outage would cause widespread disruption. That's why the system is constantly maintained, upgraded, and expanded. Newer satellites, like the GPS 3 generation, offer stronger signals, better accuracy, and improved resistance to jamming. They're built to last 15 years or more, each one a marvel of engineering traveling at over 14,000 kilometers per hour, yet synchronized to the microsecond. And the future looks even more precise. With multiple satellite systems, better receivers, AI-driven corrections, and even quantum clocks on the horizon, position accuracy may soon reach centimeter levels globally. This will unlock new possibilities: self-driving cars that never drift, drone deliveries accurate to your doorstep, and augmented reality systems that overlay information perfectly aligned with the world around you. It's easy to forget all of this when you're just trying to find a coffee shop or avoid traffic. But every time that blue dot appears, you're tapping into a global network of satellites, ground stations, atomic clocks, and brilliant algorithms. It's one of the quietest, most reliable systems ever built, and one of the most transformative. So the next time your Maps app reroutes you around a jam, or your fitness tracker logs your morning run, or your Uber arrives precisely at your location, remember, that's not just software. That's a symphony of science and engineering, echoing from space to Earth, keeping you connected, located, and on track. Thanks for joining us on this journey into the satellites behind your Maps app. If this exploration helped you see GPS in a whole new light, give the video a thumbs up, share it with someone who's ever wondered how navigation really works, and don't forget to subscribe to the channel for more deep dives into the hidden technologies that shape our world. Until next time, stay curious and keep looking up.